Today we'll go a little faster, otherwise we need to cover 14 questions. Okay. This is about getting the heat input at constant pressure. Uh, these were asked in engineering sciences in the year 2016. So in a reversible constant pressure non-flow process, heat input is given by. So what is this heat input? Whether it is equal to internal energy change or enthalpy change or entropy change or work output. So what is given is constant pressure process where the heat input is supplied. So heat input at constant pressure, we can simply say like input at constant pressure is simply change in enthalpy. Okay, still I will prove that. Starting from first law. Now, whenever heat to work, everything is related, simply start from first law. For a reversible process, we can replace this dW with PdV, and we need not bother about this dQ because there is a, of course, the heat input is directly given, so we need not write this as TDS and other thing. So we are going to fix this quantity. So, and we want to say about this heat input is equal to what? Okay. So heat input, let us keep as such. So this is your equation here. Additionally, we can also always this is about constant pressure. No, so for constant pressure, here it is. Always along with this, we'll also add this enthalpy definition. So enthalpy is U plus PV, and derivative of this will help us, and we can replace this du. So now we are getting this dkh as dq plus vdp. Now, this is also simply coming from first law. Along with the definition of enthalpy, we are getting this first law. Okay, this is this also a first law statement. Now, what is happening? This at constant p, what happen? This is going to be 0. And what is the thing happening? Constant pressure heating means dq at constant pressure. So dq at constant pressure is directly coming to enthalpy change. So dq at constant pressure, risk heat input at constant pressure is simply change in enthalpy. Okay, sometimes we'll also get this heat input at constant volume, no? That is simply equal to change in internal energy. Let us check that as well. We know this again for simply first law, and for a constant volume process, dV equal to 0. So whatever the heat addition at constant volume is simply equal to internal energy change. Otherwise, internal energy change is simply heat addition at constant volume. Okay, a related thing, this again for ideal gas, we'll see that this internal energy is simply function of temperature alone and enthalpy is simply function of temperature alone. So because of that, it will be simply like coming like CV delta T. Of course, this du is coming to CV delta T because dq is already CV delta T for a constant volume process. So for constant volume process, dq is CV delta T, that is a definition, and du is also equal to CV delta T for ideal gas. Irrespective of whether it is constant volume, constant pressure, or its internal energy change is simply function of, it depends on the initial and final conditions. So you need not worry about the nature of the process. Internal energy change of ideal gas is simply CV delta T. Likewise, for enthalpy change, it is simply CP delta T. Okay, we'll move to the next one. Yeah, this is about process with heat equal to work. That is identify the process where the heat is simply equal to work, or is simply the magnitude alone. Okay, these were asked in mechanical engineering. During a non-flow thermodynamic process, the process 1 to 2 executed by a perfect gas. Now, this statement perfect is with perfect gas is also nothing but the ideal gas. The heat interaction is equal to work interaction. Of course, when this will come, they are using this convention like uh, heat supplied is positive and work done by the system is positive. Otherwise, in our convention, delta U equal to Q plus W. So the Q and W will be of opposite signs. No? Otherwise, whenever this this thing they are using another sign convention. Otherwise, we should not worry about the sign convention. Whatever is given, you simply accept. Otherwise, what is given is heat interaction and work interaction. Simply you worry about the magnitude alone. Okay. So when this is possible, simply let us write this first law. So delta U equal to Q plus W. Again, it is given like perfect gas or ideal gas. Okay. So non-flow process. So okay, there is applicable for the non-flow process. So what is given is heat interaction is equal to work interaction. So when this is possible, always heat and work are the same. Always, let us write this in another sign convention so that this is still applicable in terms of what is it? Heat input is positive and work done is positive. So by that convention, for that convention, this is applicable. So for this, you will be getting Q and W are the same. So when this is possible, for a ideal gas, this delta U equal to 0 for a isothermal process. Now what is delta U? Delta U equal to CV delta T for a ideal gas, and for a isothermal process, it is simply delta U equal to 0. Otherwise, this heat interaction is equal to work interaction when the process is isothermal. Otherwise, we'll at least take the correct answer, take the correct answer. Okay, so process isothermal. Let us also see about this other thing. And sometime when we'll be getting this delta U and W are the same. Maybe you can think of that, no? When this delta U and W will be the same. Simply Q equal to 0, what is called as reversible adiabatic process, that is called as isentropic process. So in that case, what about this polytropic? Even for adiabatic process also, the delta U will be simply W because Q is 0. Whereas W value will be different in adiabatic, what is it, isentropic and adiabatic. For adiabatic, the it is also having irreversibility, whereas isentropic means it is completely reversible. There is a difference between adiabatic with reversibility is isentropic. Okay. And what about this polytropic process? For polytropic process, it also has relation as similar to your PV power gamma equal to constant. Instead, it will be having like PV power delta equal to constant. So the delta can have any value. And if this delta is matching to this 1.4, this gamma, then you may get this Q equal to 0. Otherwise, Q will also be there for a polytropic process. This polytropic process still have follow this, and for that, this Q will also have some value. It may be positive or negative. Okay, these are the relevant things. We'll go to the next one. This again related to the previous question. This is about the process giving maximum work for a given heat input. Otherwise, you are supplying heat, and for that heat, which process will give the maximum work? For ideal gas, okay, taking ideal gas as a working fluid, and for a given heat input, the process which gives maximum work. So again, let us take this the first law, delta U equal to Q plus W. And when this for a given Q, when this W will be maximum, if this delta U equal to 0, all this Q is going to be simply work. Okay. So for a given heat input, you'll be getting maximum work output for isothermal process. So otherwise, again, this is isothermal. Otherwise, in the previously also it worked out the similar kind of problem. Otherwise, isothermal process is giving the maximum work. And what about this isentropic? Of course, isentropic process means we won't supply heat during that process. That is what is it? Insulated or adiabatic, reversible adiabatic. And what about constant volume process? Constant volume process, there is no work involved. With PdV, dV is 0. And what about this constant pressure? How to connect these? What will be the work production in constant pressure process, and how to compare these? Of course, you can represent that in PV diagram. Otherwise, simply from again first law. For constant pressure, we have this. There will be a heat addition. No, during the process, if it is happening, there is work happening, and there will also be heat interaction. And delta U is again for ideal gas CV delta T. So you'll be having this equation like W will be minus R into delta T. Whereas for isothermal, we have this equation, and from that you'll be getting this RT ln this V2 by V1. Of course, this will be actually this ln content will be a positive content. This multiplied by delta T will be actually higher than this thing. Okay, for the given amount of heat supply. Of course, you can easily say like all this Q, whatever you supply is going to convert it to work. Only for this isothermal process. Or is this delta U, if it is 0, then maximum all the heat is supplied, converted into work. Again, maybe you can also discuss this with reference to this PV diagram. Yeah, quickly. This we have this PV diagram. I will draw it comfortably. Okay, this PV diagram. Always I will represent this curve, and this is one isotherm, and another isotherm will plot mark. And what is happening in the process for isothermal expansion? This will follow this simply this line. Whereas for adiabatic process, this is going to go in the direction of decreasing temperature. Or is adiabatic expansion, there is it's going to reversible adiabatic expansion is going to reduce the temperature. Okay, whereas this is PV equal to constant. So here it is PV power gamma equal to constant. Okay, now what to say about work? So always simply if you integrate to find the work, simply the area under the curve, and for the same pressure volume thing, we have more work with isothermal process. Or is work is more with isothermal expansion than with isentropic expansion. Of course, about constant this constant pressure process, it will go like this, but you'll be supplying more heat here in comparison. Here, whatever the heat rejection, if you want to find, you can given the data you can find. But for the heat interaction, if you see the constant pressure, the heat interaction will be more in comparison to these. So, otherwise, for the given heat input, the isothermal is giving the maximum work. That is, we can easily say between the isothermal and isentropic, constant volume, there is nothing. Of course, isentropic, during the process, there is no heat supply. In that way, you can easily rule out. Okay, only this is. Otherwise, simply you can say like isothermal expansion produces a maximum work. In the similar way, for compression, isothermal compression takes a minimum work. Whereas isothermal compression you cannot easily do because there is a perfect heat removal required. Whereas adiabatic compression you can easily do. Why it is? Adiabatic means there is no heat going out. Whereas you can easily even fast heat transfer will also lead to reversible adiabatic, provided this nicely lubricated content. So always adiabatic process is easy to carry out than the isothermal. But still isothermal is the thing you should aim for. But how to carry out this, do this isothermal, achieve this isothermal condition by adiabatic? Normally we'll go for multi-stage compression. So compress in one step, again cool it, and again compress. So by that way, actually they are trying to reduce the work requirement for large compression ratio. By having multi-stage compression, we can approach the isothermal work requirement. But always idea of going for isothermal multi-stage compression is to approach the work as expected by a isothermal process. So adiabatic process, you are trying to make like a isothermal by having multi-stage compression. Okay. Okay, now this is relevant to this work for a process. So you can go through this. Okay, you can quickly, I will quickly say about this. So we have this, yeah, this air confined in a cylinder, which is actually arrested by a stopper. And once a stopper is removed, it is going to suddenly expand, and it is again arrested by another stopper. So the process is actually not happening reversibly. Why it is? It is removed and it is suddenly going out. Otherwise, the pressure of the system and the surrounding are having large difference. So because of that, actually the process is actually a irreversible process. Otherwise, your work is simply equal to P external into dV. Okay, minus also you have. So what is a P external now? P external is actually remaining constant. Otherwise, P external should be similar, matching to the P system. Only then you can have equation like W equal to minus PdV, where you can write this P in terms of this equation of state. Otherwise, this whatever the pressure is simply the external pressure. So always your equation is minus work equal to minus integral of P dV. So this P is P external. So okay, what is a P now here? P is simply the atmospheric pressure. So what is a dV here? dV is this height difference, length difference multiplied by area. So length difference multiplied by area. Why it is area? Because volume. No? Volume changes this length difference multiplied by the cross-sectional area. Or is your formula is going to be P naught into A into what is it delta L. When this formula will come, here it is also mentioned that it is uh, adiabatic. No, suppose you try like it is a reversible adiabatic process. It is mentioned like adiabatic. Because of that, you may, if you consider like a reversible adiabatic process, you will choose this formula, because this is like this formula applicable for your reversible adiabatic process. Actually, you will be getting like P2 V2 minus P1 V1 by 1 minus gamma. Of course, 1 minus gamma is coming because of the sign convention is different here. Whereas we normally use this minus PdV, whereas the convention used is simply plus PdV. That's it. And when this formula is coming, this will come for isothermal process, reversible isothermal process. And when this will come, and it is if in case if there is expanding to a vacuum, otherwise you are having this content is otherwise you are having a container and surrounding there is a vacuum, and in that case P external is simply equal to 0. So P external multiplied by volume, whatever the volume change, you will be getting that as well. Otherwise you would have seen a container expanding in a evacuated space, that work is simply 0. And for this our condition, actually this is P multiplied by volume delta V, and this is applicable for reversible isothermal process, and this is for reversible adiabatic process. Okay, any doubt on or any discussion needed on this? Of course, similar problem we solved with a numeric in the class, in the last few classes. Okay.
Sir,
Yeah, please.
sir, it's suddenly expanding nala we are taking it as irreversible one.
Yeah. So why it is irreversibility coming? Otherwise, if you want to write this integral of minus integral of PdV, so this P is to be equal to RT by V. So that is applicable only for equilibrium state, equilibrium condition. If you suddenly remove, what happens? This suddenly it's going, and the conditions inside are taking time to again come into uniformity. Or is the closer here will be experiencing different pressure, here will be different pressure. So the contents inside are not in what is it, equilibrium condition. So you cannot write this P equal to RT for that condition. Point.
Sir, and it is also given that P1 is very, very greater than P naught.
Yeah, that is also leading to sudden expansion. Whereas normally a reversible process expect this inside and outside pressures are differing only by very minimum amount. There is a requirement for a reversible process. Inside pressure and outside pressure should not differ much. Otherwise, here also there will be a gas available, and it is available at that pressure, and slowly it is expanding by supplying heat. So they are actually irreversible process.
Okay, sir. Thank you.
Actually, what will the how to carry out a reversible process? There is the inside pressure, and there is again supported. There will be a load uh, connected to that. So that load and this inside pressure, the pressure is, if you can write in terms of force, that force and this opposing force will be differing by very minimum amount. Then only the process will be reversible process. But sudden expansion, definitely the work is still happening, but we don't know the pressure inside, and simply it is simply the external pressure and dV. Otherwise, it is working only against the external. That external pressure is very different from internal pressure. So this that's why it is simply P external into dV is. You cannot replace this P external with P system. Okay, thanks. Fine. We'll go to the next question. Yeah, normally that kind of questions were asked along. There is extra suddenly removed, or there are going to vacuum. Sometimes these statements are confusing. It is mentioned like adiabatic. Adiabatic means we choose this reversible adiabatic and we'll choose this formula. Whereas this is not thing. Whereas in one of the problem we also checked like the process is isothermally carried out, but it is expanding against different pressure. So that is again confusing. So they are trying to add that statement, but to indicate that there is no heat transfer outside. Okay, fine. We'll move to the next one. This is also a nice problem. This is about internal energy change of ideal gas from the PV curve for recipe isotherms. So there are four processes, 1, 2, 3, 4, and they are marked like this. Of course, one is some processes are expansion, some are compression, and we only worry about the magnitude. So uh, out of these processes, which is having the higher delta T. And we know for ideal gas, uh, internal energy change is simply function of temperature change, or is simply function of temperature. And where is the temperature change maximum? You can easily see now. Of course, it doesn't depends on whether you start from here or here or here. The internal energy change is simply depends on the temperature difference. Okay, so temperature difference is maximum for this process one, whereas these two, of course, it is appearing to be a lengthy process, but here the temperature level is only these two, it is T2 minus T3. So of course, which will be higher pressure, a higher temperature. If you go up, no, this is increasing temperature. So higher the temperature, always if you go direction, always from one, this 3 is at low, and this is still higher, and this is the highest temperature we have. So this one process one is having higher delta T. So higher the delta T, higher is the internal energy change. Correct now? Any discussion needed on this? Okay. So
Sir,
always,
can you explain?
explain?
Can you explain this one again, sir?
Yeah, right. Say here we have isotherms. So these are all constant temperature curves. Okay, and there are various processes happening. One, what is the change here from this T3 to T1? So this T3 to T1, always we have higher delta T, correct? Always, so assume in terms of numeric, if you want to, this is 10, 20, 30. So you have 20 degrees Celsius the difference for this one, whereas here this is simply 10 degree, this is also 10 degree, this is also 10 degree. Correct? Otherwise, the higher the delta T, higher is the energy change. Otherwise, delta U is simply, of course, it depends on the mole, and it is like the same amount of contents. Okay. So it is simply the CV delta T. So delta T is higher for this process one alone. Though you may say like this is a lengthy process, this is lengthy process. So it depends only on the initial and final temperatures. So initial and final temperature is higher for this process one, whereas, so what is the temperature difference? This is T1 T2, and this is the same thing, T2 T3. Otherwise, this process 2 to 3, 2 and 3 will have the same delta T. Okay, there is one thing. And additional question also can be asked, because same delta T is leading to same delta U. Internal energy change for these two processes are the same, 2 and 3. And 4, the change is only from T1 to T2, whereas here the change is from T3 to T1. Of course, we are checking only on the magnitude. Don't worry about the direction. So here we have the maximum delta T.
So there is a change from T1 to T2, but not T2 to T1. So
where here T, this is changes.
second process வந்துட்டு T2 to T3.
Yeah, correct. T2
third process வந்துட்டு T3 to
T2, correct.
அதே மாதிரி இங்க T2 T1 நடக்காது. Process இங்க fourth process one side.
That is happening from T1 to T2. Okay. This is this delta T is lesser. Maybe say if you want to say about 2 and 3 are having the same internal energy change. Okay, fine.
இப்போ வந்து T2 ல இருந்து T1 அந்த process நடக்காது.
T2 ல இருந்து T1. T2 ல இருந்து T1. Yeah, this is process happening. This process. See, we are interested in. I'll write the equations comfortably. So we have this delta. So delta U is simply equal to CV delta T. Correct? So which is having higher delta T? Delta T is, at least you can easily say, if you have another line, that if you go along this, temperature is going to increase. Okay. Fine, no? Yeah,
Yes.
this was a nice question. That's why I taken this question. Recently asked in our engineering sciences. Good? Convinced or any more?
Yeah, sir. Actually, my doubt is process 1 வந்துட்டு T3 ல இருந்து T1.
One is
process 1.
Yeah, fine, correct.
So அதுக்கு தான் வந்துட்டு higher delta T.
Yeah, we have a higher delta
doubt
T.
என்னன்னா இப்போ நம்ம T1 to T2 process நடக்கும். T2 ல இருந்து T1 process நடக்கும். Change.
Yeah, see, simply delta T alone is matter here. CV is the same. Okay, delta T is higher for this. Simply take that.
Okay.
Good. Thanks. Good. Yeah, this is another interesting problem. This is about getting the network from PV diagram. The network output, we need to find this for this 1, 2, 3, 4, 5, 6. Service, we have this process like 1, 2, 3, 4, 5, 6. Okay, this is a cycle, some kind of cycle they have. These were asked in engineering sciences in the year 2007 as a 1-mark question actually. So can any of you say this answer? Of course, I used to ask the answer, very simple answer only.
Area enclosed between the cycle, so it will be
cycle.
200.
If you say like 200, okay, it is like this is 1 and this is 1. 1 into 1, 100 and 100 plus 100 to always bar into meter cube. You can convert into, that will be coming in 100. That is fine. But 100 plus 100, there is 200 correct in terms of work thing. But we should also worry about the sign here. So here this part, no, this part is like clockwise direction, which means this is what is it? The power cycle. Correct? This part is a power cycle, and this part is like a compressor. No, to the compressor, what we'll do? We'll no, to the compressor, we actually will be having this supplying work. Supplying work. Otherwise, like a refrigeration cycle, this is a power cycle. So otherwise, we have this combination. Both are having the same magnitude. So this is actually this step is actually producing work, and this step is actually consuming work. So totally is going to be 0. So that's why we have given this kind of answers. Is it okay? Correct?
Yes, sir. I get it. Yeah.
Okay, good. So here, very important thing. No, that's why these questions are nice. Actually, idea is you should also worry about the direction of this process. So here we have combination of what is it? Clockwise and anti-clockwise. Correct? No, this is anti-clockwise. So always here it is nothing but it is a refrigeration cycle. You know about this vapor compression refrigeration cycle. You will have this kind of direction, no, arrows. And for Carnot cycle power plant, you'll be having this positive direction. So this is network is positive here, and network is it is demanding work. This is producing work. So totally, actually, it is going to be 0. Good. So there is some learning here, no? Good. We'll move to the next one. Okay, you can go through this. This is about heat transfer of a cycle from the PV diagram. Normally we used to get this W from the diagram, but how to get Q from the diagram? Okay, there is a task now. A fixed mass of gas undergoes 2 different cycles, M and N. Okay, this is M and N. PV diagram is available based on the information. Which of the statement is always true? Which is always correct? Heat input in cycle M is equal to heat input. Based on this diagram, only we can say about delta U is simply 0. Delta U of any cyclic process is 0. And what about this area? I think area wise they are similar. The same thing. Only here it is this part, and otherwise area wise the same. Which means what can you say about this work? Network is the same in both the cycles. Of course, our sign convention also you have to now check. So here, this is like a what is it? Clockwise. So it is a power plant cycle. So whereas here, here also clockwise. Okay, in terms of that, what is it? This also a power plant cycle. So both are magnitude wise W net. Or is W network is same for both the cycle. Correct? And from that, can you say about heat? Delta U for both the cycle are the same, 0. And delta W for the both the cycle are also the same. So which simply is delta U equal to Q, simply Q plus W. So since W is the same, then Q will be of the opposite, simply. Or is Q for the both the cycles are the same. There is a thing we can conclude. And what about the efficiency? Thermal efficiency of M is equal to thermal efficiency of N. How can we say about the efficiency? Of course, efficiency demands you to know the values of course, net work divided by heat supplied. Okay, there is a efficiency. So any efficiency definition is what is the output by input. So input is how much of heat is supplied at high temperature. So is your efficiency, or is if you want to say in terms of thermal efficiency, simply defined as work output, or is here it is net work divided by heat supplied. So how to say about the heat supply? The heat supply depends on these pressure temperature levels. Of course, based on the thing, we can say like here the these points will have higher temperature, no? In comparison to this point is at a higher temperature. Uh, of course, we cannot say simply from anything about the efficiency. Of course, efficiency will be definitely different because heat requirement of heat supply of this M and N are different. Heat supply means not the net heat. We are worrying about the heat at the high temperature. Whereas QH of M and N are different. So efficiency will be definitely different. So what is the thing we can say is net heat transfer in cycle M is equal to net heat transfer in cycle N. Whereas this is the thing. This is the correct answer. So far we are discussing about this first law and something about heat work. Now we are going to this ideal gas. Ideal gas is a nice thing, and with PV equal to nRT, or when do you have N and when do you have simply PV equal to RT, or is V is molar volume. Sometimes R will also have as universal constant, or sometimes they are also giving like a characteristic gas constant. So what is the difference between universal gas constant and characteristic constant? R is simply in mole per joule per mole Kelvin, there is universal constant. If it is available in joule per kg, then you need to get that from the universal to again molecular weight. What is it? Dividing or multiplied. Check for a unit, and you have to convert that joule per mole to joule per gram or kg. So that is the difference. Okay, related thing. Please go through. Let us try to answer this. This is about the ideal gas, the conditions and the processes. Of course, this is taken from I think mechanical engineering. No? Okay, in the recent time only. So, which of the following statement is false? Or is only one of the statement is false. Sometime in the recent time, they are also asking like multiple select questions. So, in that case, it will be very tough. So, you have to select all that applicable. Then only you will be awarded with mark. Otherwise, it is like all or nothing. You have to answer all the options. Otherwise, you won't be given with any mark. Okay. So, which one of the following statement is false? Okay, let us see with a simple statement. For an ideal gas, enthalpy is independent of pressure. So this is a correct statement. Otherwise, this is not a false statement. Simple. Otherwise, this is ruled out. And for any real gas behaves as an ideal gas at sufficiently low pressure or sufficiently high temperature. So what is the condition for a ideal gas? Otherwise, we'll write like PV equal to nRT. And when do you consider when this equation is valid, you should have this low density, or is density equal to our N by V, which is moles per volume or mass per volume. Okay, so N by V will be like P by RT. So at for low density, you need to have low pressure or high temperature. So at low pressure or is at very low pressure, any gas can be considered as ideal gas, or very high temperature, any gas can be considered as ideal gas. So what is that? A real gas behaves as an ideal gas at sufficiently low pressure or sufficiently high temperature. Fine. Otherwise, this is also a correct statement. So this is not a false statement. Okay. So these two are ruled out. And what about the lengthy statements? Let us go through. Maybe we'll see. For an ideal gas undergoing a reversible polytropic process, PV power 1.5 equal to constant. The equation connecting the pressure, volume, temperature of the gas is PV equal to mRT. R is the characteristic constant, M is the mass. This is applicable for the process. In addition, every point is also satisfying this relation. That is correct. For an ideal gas, this is always valid. Irrespective of any process, the states are connected by PV equal to mRT or nRT. Okay. Whereas the process path is given by PV power 1.5 equal to constant. This is For that, the polytropic index is okay 1.5. Otherwise, this is also okay. It's not a wrong statement. This is a right statement. So, which is the correct wrong statement? Okay, let us see again. For a real gas going through adiabatic reversible process, otherwise this is a real gas. No, real gas means not a ideal gas. Okay. So for that, the process is given by PV power gamma equal to constant, where P is thing, V is volume, and gamma is the ratio of specific heats. Is it valid? No, this relation PV power gamma equal to constant is valid only for ideal gas. Okay, whereas this is said like for a real gas, or is for reversible adiabatic process, PV power gamma equal to constant only for ideal gas. Of course, reversible adiabatic, okay, but it should be a ideal gas. Otherwise, this is the correct false, otherwise false statement. Otherwise, again, I will try to prove that how this PV power gamma equal to constant is coming to ideal gas. Okay, the work is simply Q plus W, and from that we will write in terms of differential. And for a adiabatic, dq equal to 0. For a reversible, dqw will be minus pdv. And for ideal gas, we can write this. So we are having this equation for the process. And since it is only having like a pressure and volume and temperature, we can also write this again with in terms of enthalpy. Enthalpy is U plus PV, again expanding. So we have d again for ideal gas dH equal to Cp dt. So we are having one another equation for the thing. So this is Cp, this is Cv dt, and this is Cp dt, and these two are valid for the process. Okay, we don't say anything about that. Otherwise, we are simply taken the condition of d equal to 0, and the same thing we have applied here. Otherwise, we have this definition of enthalpy, and replace this du. Otherwise, we have this, and dq equal to Cp dt, and du equal to already Cv dt, and so these equations are already retained. So using 2 in above, that is what is that 2? 2 is CV, for CVDT we replace with minus PdV. So now we are having these things are getting cancelled. That is for the same process, this equation is also valid. So now we can take the ratio of this thing. So Cp and Cv are getting now. So Cp by Cv is gamma. There is a definition. Okay. So Cp by Cv is now coming to, now we are getting the equation which is PV power gamma equal to constant. Otherwise, how this is coming? Wherever P were there, now we are trying to replace that with service here minus PdV. Okay, minus PdV is there. And where is that? Where actually we have used ideal gas. Otherwise, these equations, this dH equal to CPDT is applicable for only ideal gas. Otherwise, dH is H is a function of pressure and temperature in general. Whereas H is equal to only a function of temperature only for ideal gas. As like that, this is also applicable only for ideal gas. From that only this final derivation is coming. Final relation PV power gamma equal to constant is coming. Whereas PV power gamma equal to constant is applicable for a reversible adiabatic process undergone by a ideal gas. Whereas this PV power gamma equal to constant you cannot apply for any gas. It is applicable only for ideal gas. And again, a reversible adiabatic process. Okay, clear? This is about getting the constant of cubic equation from critical point data. Engineering Sciences 2014. For this, we are also given this equation of state, and we are given with critical volume and critical temperature. So we are given with the critical volume and critical temperature data, and the value of the gas constant R is given. So value of A. So how to get A? And additionally, they are also giving one mention. Note that the critical point is the point of inflection on the critical isotherm. Otherwise, at the critical point, which is actually a point of inflection on the critical isotherm. So what is the meaning of point of inflection? So you have this curve, the PV curve, and you have this. So this curve actually is having change of slope. Otherwise, it is neither maxima nor minima. For a for that point, that is what is called as a, that is for the critical isotherm, any cubic equation of state is supposed to satisfy this equation, which is the first derivative of that PV and second derivative of PV curve is equal to 0. That is at Tc equal to 0. Otherwise, dou P by dou V as well as dou square P by dou V square, both are 0. Otherwise, for the saddle point, these things are valid. Whereas for maxima or minima, of course, again, first derivative will be 0, and second derivative will be positive or negative, whether it is minima or maxima, like that. No, so now it is a saddle point. For the saddle point, second derivative is also 0. Okay, by using these 2 points, using these 2 relations only, we are used to getting these constants A and B of van der Waals. The same thing, of course, van der Waals is also a cubic equation of state. Now here we also have a cubic equation of state. Or is for any cubic equation of state, this is valid. Okay, now you are going to use this condition, and of course we'll first take the first derivative, which is actually writing this equation in terms of P. So P is available here. Now take a derivative with respect to V at constant T. Simple only. Otherwise, this is 1 by V. So 1 by V will be otherwise V power minus 1. So V power minus 1 divide by multiply by, otherwise we'll take simply 1 by V derivative. And here it is 1 by V square. So for that already V power minus 2 is there. Let's say 2 is there. Okay. So this content. And of course, this is T equal to TC. Okay. And is what we are doing, we are simply substituting here, and from that A is available. So it is coming like RTV by 2, or is RTC VC by 2. Simply substitute this R and TC. And again, whenever you are using this thermodynamic thing in terms of temperature to be used in Kelvin scale. Okay. Sometimes they, to confuse, they will again give in Celsius, and they will also say like R equal to 8.314 joule per mole degree Celsius. No, degree Celsius rise or degree Kelvin rise are the same. Don't worry about that. So the answer is 186.5. Fine. Always the thing I want to say here is you can make use of this condition for the at the critical point and evaluate the constants. If it is 2 constant, you'll sometime you will be also taking the another derivative, which will be adding to lengthy. Okay. Whereas this was very simple because of A is coming directly from the first derivative alone. And sometime given this cubic equation, they will also ask you to get the vapor volume and liquid volume for the pressure of saturation pressure. Otherwise, you'll be given with the pressure temperature data. Now, given the pressure temperature data, solving for volume is actually involved because it's a cubic equation. If you want to solve that, you'll be getting 3 roots, but actually one of the root will be complex root. So no need to worry about that. So there will be again 2 positive roots. So which root is vapor volume and which root is liquid volume, or how to get that? Of course, higher root is vapor volume and lower root is liquid volume. You can easily say that. And how to get that upper root by solving and where to start? No, normally we'll use this trial and error solution, or you can use this your Newton-Raphson technique. And to get the vapor volume, you can take this or to get the saturated vapor volume. Suppose there is a constant here B, and you have to take you have to start with V is equal to RT by P, which is or simply initial gas we are taking from ideal gas equation. Using that, you are getting a volume estimate that will be giving the value of the saturated vapor volume. To get the liquid volume, suppose assume this is equation is having V minus B. So you start with the value of B as the initial gas and get the final volume. So that will be giving you the lower root. That is, to get the lower root, start with this molecular, the B. Normally we will account for the volume of the molecules, volume occupied by the molecules. So volume occupied by the molecules, in the molecules are closer. So your volume of the liquid will be closer to B. Okay. Whereas for the gas, it will be closer to ideal gas equation. Okay, there is a related points. We'll move to the next one. So now we are going to the second law. So far we are taking this basic concept, first law and PVT. Now onwards, second law and thermodynamic relations and flow process. Okay, this is involving this. Some at least you have to go through carefully. This is about finding the feasibility of a thermodynamic cycle. Asked in engineering sciences, actually they were giving 2 marks for this question. The cycle 1, 2, 3, 1. So always we have only 3 steps. Okay. 1 to 2 is a constant pressure expansion. Or is 1 is constant pressure expansion means the there will be expanding, so you can also supply heat. There will be a heat supply and work production. That is, this is heating as well as working. Heat supply at constant pressure will happen naturally, and this process is going to happen at expands. Otherwise, there is no mention about heating, so you can also consider like there may be heating available possible. Okay, what about this thing? 2 to 3 is reversible adiabatic expansion. So reversible adiabatic expansion means there is no heat supply. Okay, whatever is already there, it is expanding. So otherwise, in this 2 to 3, there is no heat supply. Correct, no? And what about this 3 to 1, which is irreversible adiabatic compression? Here also adiabatic, so there is no heat supply. Or is heat, going in, or is there is no heat interactions in steps 2 to 3 and 3 to 1. Whereas in 1 to 2, there may be heat interaction, which is not very clearly given, but you can expect there may be heat available. Then only the process will follow. No, otherwise, to make it as a cycle, there should be some heat supply. Then only it will be producing work. So otherwise, you can definitely consider this is having a heat interaction. Okay, of course, 1 to 2 is constant pressure expansion. Heat addition is happening to the system. There is definitely that should be there. Then only there will be what is happening. There is a work production. And 2 to 3 is a reversible adiabatic, only work production by the system. And 3 to 1, again irreversible adiabatic compression. This is work done on the system. Here, what is work production of the system? In the first step also work is done by the system. There is constant pressure expansion. Okay. But here, this 3 to 1, in what way it is going to think? Because of irreversibility, some more work will be required than that of the reversible process. That is the only thing. So otherwise, this cycle is possible. Okay. Otherwise, let us now evaluate this statement. This cycle is feasible and can deliver net positive work. Is it possible? According to first law, okay, it is seeming like possible. But what about, we should also check with the second last requirement. Okay, now this we cannot easily say now. The cycle is impossible according to the Kelvin Planck. We will come to that. The cycle is impossible in accordance with the first law. But first law requirement is possible. Otherwise, there is a heat supply, and these are all work, everywhere work is production. Otherwise, according to first law, there is no violation of first law. We can say definitely this is otherwise the cycle is not violating first law. In what way? Because there is a heat supply happening in this step 1 to 2, and here everywhere there is a work production, and because of a cycle, and there will be again heat. Otherwise, it is not violating. We cannot easily say about it is violating first law. Otherwise, it is not. We cannot say about this impossible. Otherwise, it is possible. The cycle is possible in accordance with wire. Otherwise, it is not. We cannot easily say like it is violating because heat and work are there. Okay. So otherwise, it is possible. And what about the net work of this cycle is 0, because what to say about this network of the cycle is 0 because of there is no heat transfer, that itself is rolled out because everywhere work is done. This work is expanding, and again another expansion, and again another expansion, another compression. So there is a network is there. Otherwise, this also we cannot rule it out. What about this cycle is impossible? That will come to. The cycle is feasible and can deliver net positive work. Net positive work is possible. Okay, let us see. But okay, there is always a heat rejection required for the. Okay, here. What is happening about the? What about the heat rejection? No, everywhere. So here it is heat supply. This is adiabatic expansion. There is no heat interaction, and here also no heat interaction. So heat is supplied. Correct? Heat is supplied possibly at this process. But where is the heat rejection? In any thermodynamic cycle, there should be a heat absorption as well as heat rejection. So here there is no heat rejection possible. So this is like a cycle which is converting all the heat into work without rejecting any heat. Which is nothing but the statement of Kelvin Planck. Now Kelvin Planck says like for any thermodynamic cycle to operate, it cannot convert all the heat into work. There should be a heat rejection. Hence, there is no heat rejection mentioned, or there is no heat rejection possible in this process. It is simply violating the second law. And we can say like the cycle is feasible. Or since it is violating second Kelvin Planck, the cycle is definitely not feasible. Or we need to identify the correct statement. The cycle is impossible. Or this is also not possible. The cycle is not possible because this is automatically, or if this is correct, this is wrong. Okay, nice statements. We should understand every statement. It is violating Kelvin Planck because there is no heat rejection. Kelvin Planck statement. Now, what about the other statement? Clausius statement. According to Clausius statement, heat cannot go from low temperature to high temperature automatically. Kelvin Planck you consider like a heat engine, and Clausius statement you can consider like a refrigeration. For refrigeration, there should be a work supply. You have to supply work, then only the heat at low temperature will go to the surrounding, which is at a higher temperature. This is about delta U and delta S changes for heat transfer. For irreversible heat transfer from hot body to cold body, that means there is a entropy, hot to cold. No, what will happen? Entropy for one it will be decreasing, another it will be increasing. What about the overall entropy change? Overall entropy change definitely will be a positive for a irreversible heat transfer. So what is the meaning of irreversible heat transfer? We are simply allowing the heat to flow we have a high temperature, low temperature. Whenever this high temperature and low temperature are there, you should try to get work out of that heat exchange. During converting some amount of heat into work. If you do that, there is actually a reversible heat transfer. Otherwise, your heat engine, Carnot engine is doing reversible heat transfer. So whereas there is no mention about engine, simply it is hot body and cold body, they are exchanging heat. So hot body's entropy will be reducing, cold body's entropy will be increasing. The total entropy will be actually coming, total entropy change will be actually positive content, positive. Okay, otherwise you can simply say like entropy change is, total entropy change is positive. What about this internal energy change? The internal energy change of one body, that is equal to internal energy change of the other body. That is, one is giving heat, another is taking heat. So energy balance is always valid. Say for heat transfer, one is giving energy, another is taking energy. So energy balance is valid. Otherwise, this delta U for the total is simply zero. Otherwise, this is not possible. And what about this internal energy entropy change? We won't have this entropy, total entropy decreasing. Of course, total entropy will be zero. For which one? For this, if you do this heat transfer by having a engine, and you are still making a heat transfer, no? Heat from high temperature is going to low temperature. Not all the heat, portion of heat is converted into work. So that is actually a reversible heat transfer. So for that, your delta S will be equal to zero. Otherwise, for any irreversible heat transfer, this delta S will be definitely positive. Of course, delta U is always equal to zero. Whether it is reversible or irreversible, delta U will be still equal to zero. Okay, we'll move to the next. This again related to, we are moving to now from a combination of second law and thermodynamic relations. So there is a PV diagram. Nice rectangle is given, rectangle or square, whatever you want to say. Okay, and we have to represent that in TS diagram. So for a ideal gas undergoes process. So what is the process 1 to 2? You can easily say it is a constant volume process, and 2 to 3 is a constant pressure process, constant volume. Nice. At least if you know about these two steps, enough. Other thing automatically. Okay, one is increasing, another is increasing. There is increasing pressure and increasing volume. The other two are simply opposite. Only these two alone we need to consider. From that, we have to say about the TS diagram. And for this, we should know the relation for delta S. No, there is PV to TS. There is what is there is this is this kind of. So here it is delta S. No, delta S is set like 0, whereas this is temperature difference. So for this, now let us get the equations for entropy change. Otherwise, these are all nothing but change, entropy change and temperature with dt by ds. If you get that, you can easily get this graph. Otherwise, dt by ds of your this ideal gas. Say for ideal gas, say for, first we will present this mnemonic diagram. So simply pass GVHTU, okay, pass GVHTU, and have these arrows. And what is this? Yeah, first let us, we also need this entropy change with, there are constant volume as well as constant pressure processes. So you can consider this S as a function of T and V as well as S as a function of T and P. So by considering S as a function of T and V, ds equal to dou S by dou T at V and this thing. Okay, this dou S by dou T at V is simply CV by T. Now why it is? Because this ds is equal to dq by T, and ds at constant volume is dq at constant volume, which is CV. So from that we have this thing. Okay. And what is this dou S by dou V at T? Dou S by dou V at T is simply minus dou V by dou T at P. Dou S by dou V at T is dou P by dou T at V. That is connecting two verticals, so no sign change. Okay. Dou S by dou V at T, that is equal to dou P by dou T at V. Fine. And what is dou P by dou T at V for an ideal gas? Simply that is equal to R by V. So now we have CV ln T2 by T1 plus R ln V2 by V1. Okay, we can simply say take in terms of ds itself. So what is how to 1 to 2? 1 to 2 is constant volume. So for constant volume, this is not there. So for ds by dt is a positive content, correct? Otherwise dt by dvs also, dt by ds. No, this is like your say dt temperature also changes there, and ds also. Now dt by ds is positive. No, dt by ds is dt by ds is simply equal to T by CV. dt by ds is a positive, which is only for this. And what about the process 2 to 3? 2 to 3 is constant pressure. So for that, let us consider this S as a function of T and P. So always we'll be having Cp ln T2 by T1 and R ln minus R ln P2 by P1 in terms of integrals. Always this is the thing. And for constant pressure process 2 to 3, so we'll be having this as 0. So what is this dt by ds, which is available now? We have this dt by ds. This is dt by ds, or a slope of this. dt by ds is positive for that diagram. So dt by ds, what about this dt by ds required? dt by ds also positive here. Otherwise, this simply matching. And this is going like this, or these are all positive thing. And what about this thing? Slopes, they are going to be negative slope. Otherwise, these are all positive slope, and this will be negative slopes. Negative or okay, still okay, positive slope. No, okay. Otherwise, they are decreasing. Otherwise, you can say about this positive slope and process 2 to 3 and 4 to 1. Otherwise, for the first and 1 to 2 and 3 4, 1 to 2 and 3 to 4. Otherwise, of course, we have this thing, and they again the same thing. Of course, they are going to come to this entropy. Of course, decreases from 3 to 4. Like that, here it is entropy increases. Okay. Otherwise, you can easily match this and this. Otherwise, given this PV diagram, you should be in a position to get TS diagram for the, at least for the ideal gas. So what is the TS changes for throttling of ideal gas? Whenever you take this ideal gas, throttling refers to, what is it? Constant enthalpy process. So delta H of ideal gas. Now delta H of ideal gas, now what is the meaning of the throttling? Reduction of pressure. So enthalpy change, pressure change. Will there be any change of enthalpy because of change in pressure? Enthalpy change is function of temperature alone. So since because of pressure change, enthalpy will not change. Otherwise, enthalpy change is not there. What is the meaning of that? Inlet and exit temperature will be the same. Otherwise, for ideal gas, there is no effect of cooling or heating. The temperature will simply remain. Enthalpy, since it is delta H is constant, delta H is equal to simply Cp delta T. Delta H is not constant, or delta H is simply 0. That is the meaning of throttling. Enthalpy at the inlet and exit are the same. So since delta H is 0, delta T also 0 for ideal gas. So where is delta T 0? Here delta T, yeah, here is this process 1 to 2, the same temperature. So there is 1 to 2 represents the throttling of ideal gas. Okay, what about these conditions? So these are all, this is what is called as reduction of temperature, from 0.1, 0.3, actually there is a cooling. This process is possible. What is it? Of course, any throttling process is a irreversible process. So there is a increase of entropy. So this is possible for a cooling step. Okay, or is temperature decreases. Correct. From this temperature it is decreasing. What about this 1 to 5? 1 to 5 actually not possible, because a decrease of entropy will not happen for this throttling. Okay, throttling is a irreversible process. It is going to increase the entropy. So this is a impossible step. And what about this 1 to 4? When this 1 to 4 will happen? Actually, which is for a isentropic process, or we call it as, instead of throttling, if you send through a, or instead of sending through a valve, if you send through a turbine, there will be constant entropy process. Or given the diagram, you should also relate the possible processes. Whereas 1 to 2 is the correct answer here, which is throttling of ideal gas, and 1 to 3 is possible for the real gas. Even for real gas also there is no need that there should be a reduction of temperature. There is also an increase of temperature also will happen. So in that case, it will be like it will go like this. Otherwise, there is increase of temperature, still there is an increase of entropy. Otherwise, this process 1 to 5 is impossible one. So if you have a heat gas temperature for which the temperature is increasing, for Joule-Thomson expansion need not always produce cooling, but normally we expect cooling. But there are also there won't be any change of temperature, not only for ideal gas, even for real gas also the temperature change may not be there at some point, what is called as inversion point. Otherwise it may be getting heated up or getting cooled down. Okay, and this 1 to 4 is for isentropic process happening in a reversible system, what is called as a turbine. Okay, here this problem were similar problem were discussed, 2-3 problems were discussed in the past video content. You can go through them. Still, I am going to highlight what is the essential thing here. So always here we have a pipe flow. From that, it is going to connect. It is connected to a reservoir or a tank to which the gas is going, and it is going to fill that tank. Okay, there is a process. Or we have a compressed air at this pressure and temperature. It is going through a pipe, large pipe, and it is connected to a evacuated tank of this volume. Okay, this volume and all doesn't matter. And what is happening is there is a change of internal energy of the tank contents. No, initially there is no energy and it's keep on getting filled. Otherwise, it is kind of a unsteady process. Why it is unsteady? It is initially no content, and with time your mass and energy are going to rise. And whereas the supply is a steady supply and it is coming at the same enthalpy, it is coming large content, so it is coming at the same pressure and temperature. So this is the equation to be solved actually. So here if you say again mass flow rate multiplied by time difference, so you'll be getting in terms of mass multiplied by enthalpy entering equal to mass into internal energy. Or else you'll be having, like, if you say in terms of air, say MC, your MCP T will be equal to MCVT equal to like MCPT. Otherwise, at last you will be simply connecting like the T of the receiver, otherwise T of the tank will be equal to T of the tank contents will be coming like gamma times T of the reservoir. Otherwise, because of filling to the tank, actually there is a enthalpy coming in and it is going stored as internal energy. So enthalpy is Cp delta T and internal energy is Cv delta T. So what is going to happen? Your Cp delta T and Cv delta T, if you try to balance, and there will be your tank tank temperature will be actually found to be higher than the what is it, the reservoir. From your reservoir is coming at only 400 Kelvin, but the tank temperature is found to rise because you are also adding not only this, you are adding this enthalpy and it is going to store as internal energy. Otherwise, here in what way this is H is added, H is equal to U plus PV. So that flow work, no, that is going to store as internal energy. So that that PV is going to rise this internal energy. Otherwise, your temperature of the tank will be higher than the this reservoir. Okay, or is simply 400 times 1.4. There is a gamma for this. So 400 times 1.4 is the answer. provided there is no contents inside. Suppose there is already contents inside, and again this formula will be coming. In addition, you should also make the proper balance on the mass. Okay, initially there is some mass, because of that slightly extended equations will come. Okay, you can some similar one example is already posted. Please go through that. Okay, this kind of problem were quite often asked, at least the tank filling problem from a reservoir. This without much solution calculation, you can simply write the answer. Of course, the derivation is given. You can go through that. Okay, I'm now available for any of your questions on this Thermo 1 at least.